All right. Good morning. All right. So last day, we started talking about the domain of a function, or kind of working on the domain a little bit more than we have in the past, and we'll keep coming back to the domain. So remember, the domain is the all possible inputs into a function. And I think, well, I know because I flipped back to our notes from last day, and we had ended on these problems here in section 1.4. And I'd said, try 13 and 14 for next day. And so that's where we'll start. Okay. So in terms of review, we talked about factoring quadratics. I'm pretty sure that was last day. And that's going to be a really important, even if it wasn't last day. Yeah, so we talked about how do we use the quadratic formula to factor a quadratic equation. And so that means that we won't have to memorize those factoring formulas or anything like that. If we have a quadratic, we can always use the quadratic formula to factor it. And so that's going to be really, really useful, and we'll use it again today. So I'm not going to do an example to review because it's coming at us pretty hard. So, but I will put it on the list, right? Using the quadratic formula, which was x is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. To factor a quadratic, which has the form ax squared plus bx plus c. So the first thing is, there. My bees aren't cooperating today. The first thing is recognizing what is a quadratic. It's anything with an x squared as its highest possible x. Now, just this is also a quadratic, right? We don't have anything to factor it with, right? So there's no need for the quadratic formula, but this is a quadratic, right? Because it's got that x squared, because technically it's 1x squared plus 0x plus 0, right? So just being able to recognize quadratics is going to be really, really useful, because then you can use the quadratic formula to factor them easily. And I would say in calculus, we don't really go beyond quadratics for factoring. So if you are able to factor a quadratic, you're really, really solid for factoring in general, right? And then remember, if you have more than 4 terms, or 4 or more terms, I should say, then you can try grouping and you can try different tricks to factor. So that's back in the previous section, or maybe it was 1.3, I can't remember. But anyways, so this, I'll even highlight it. How about, right? Big player. Then we started talking about the domain of a function. Okay. We eliminate any input values from the domain that make us divide by 0. That's not allowed. That's illegal math, right? make us take the square root of a negative number. We can't do that, right? So these are all illegal math moves, so things we can't do. For now, we only have 2 things in our checklist for the domain. Later on in chapter 4, we're going to introduce a third one. But by then we'll be so well versed in the other 2 that adding another one won't be a big deal. So the domain of a function, we remove any values of x that yield division by 0, division by 0, right? That's illegal math. And, or, I guess, the square root, or sorry, the even root. Typically, we're just dealing with the square root. So that's why I default to the square root, but it's technically the even root. The even root of a negative number. I can take the root of 0, right? So this is only values that are strictly less than 0, right? But you can kind of talk your way there. Okay, so by way of example, let's do 13 as part of our review. Okay. First thing you're going to see here is I've got a quadratic and I've got a quadratic. Okay. Now this top one, we can plus minus, yeah. Just checking in my head. We can absolutely use the quadratic formula. In fact, let's try it, and then, but you might also recognize, okay, so in 13, right, x squared plus 1 over x squared minus x minus 2, here, notice that this is in the format of x squared plus 1 squared, right? 1 squared is just 1, right? Which is one of those special factoring, I feel like. So here's the deal. I don't actually have those special factoring formulas memorized. I don't need to, so you don't need to. Because I always end up using the quadratic formula. But if you want to have them memorized, by all means. So here in section 1.3, if you have something, it's not. Okay. I'm just looking for an x squared plus b squared, but we don't have it. Great, even better. I guess I should have checked that before. Whatever. Just so it's not confusing, I should probably memorize my special product formulas. Anyways, so what we can do here is, okay, so the question, let's go back to the question, find the domain of the expression. Okay, so remember what we said about expressions and equations? This is an expression because there's no equal sign, right? What we said before, to factor a quadratic, we have to set it equal to 0. And that's actually not a problem because here we've got division. And what we're trying to avoid when we have division is we want to avoid divided by 0. So setting this thing equal to 0. So the domain here, for our domain, we need to avoid division by 0, right? I don't see any square roots or any roots at all, right? And so all I'm trying to avoid here for the domain, sorry, I was trying to factor and do fancy stuff. That's okay. All I'm trying to do is to avoid division by 0, right? And so what I need for my domain is I need x squared minus x minus 2. Here I'm catching myself because sometimes I'll say not equal to 0, okay? Or sometimes it's easier to say, okay, I'm going to force it to be 0, and then I'm going to pull those values out. So it actually doesn't matter in this case, as long as you keep it straight, which one you're doing, right? Force it to be 0 and then pull those values of x out, or say, okay, it can't be 0, so what values make that happen? In this case, I think it's easier to figure out which values make it 0 and pull those out. So here we've got a quadratic, right? This is a quadratic with a equals 1, b equals -1, and c equals -2. Okay, so we can use the quadratic formula to find where these, what values of x make this equal to 0, right? Remember the quadratic formula shows you where it crosses the x-axis, right? So where is this thing equal to 0? All right, so I'll put it on the next page here. X is -b plus minus the square root of b squared minus 4ac over 2a. So x is -1 plus minus the square root of -1 squared minus 4 times 1 times -2. Making sure you keep all your negatives on there, because missing a negative would mess everything up, right? So just be really careful when you're plugging in your values. Plug and chug, as we like to say, right? Once you're here and you have your A, B, and C, then you plug them in and you chug away, and you can just calculate them. All right. So some calculators even have a quadratic formula function. I'm sure this one does. I just don't know where it is. I don't really care. It's not that hard to calculate, but might be worth looking into if you've got a calculator. If you're just using the Desmos app, I don't think it does it, but you can check it out. So -1 is 1 plus minus square root of 1 minus 4 times -2 makes -8, so plus 8 all over 2. Maybe I'll shorten up that square root. In the next step, I'm not going to show that this simplifies to 9, right? The square root of 9 is 3, so I'm going to jump right there. X is 1 plus minus 3 over 2. Remember what we said, if we get a negative in the square root, remember we can't do that, then there are no solutions, right? Then there are no values of x that make this thing 0, which would be fine, right? Then there's no values to pull out from the domain. In this case, there will be some values. So, all right. So we have x is 1 plus 3 divided by 2, and x is 1 minus 3 divided by 2, right? Remember, parabola is going to cross, if it crosses the x-axis, it'll cross at 2 points. We saw one special case where it kind of bounces off of the x-axis, right? That's going to be very rare. We saw one, so we know what it kind of looks like, but in general, we're going to have 2 values where it crosses the x-axis. So x is 1 plus 3, which is 4, divided by 2, which is 2, and x is 1 minus 3, so -2 over 2, -1. That means that when x is -1 or when x is 2, we get 0 in the denominator. So what that says is that we have to pull these out of the domain. Since x equals, I'll do them in order, -1 and x equal 2 yield 0 in the denominator, we need to remove them from the domain. Okay, great. So what's our overall domain then? Well, if we go back to our formula or our expression here, anything can happen up top, okay? And then we figured out what values of x, -1 and 2, and you can plug them in, right? -1 squared is 1, minus -1, so that's 1 plus 1 is 2, minus 2 does equal 0. Surprise, surprise. That's what we forced it to solve, right? So, so -1 and 2 both give values of 0, so we need to eliminate those. But otherwise, any value from -infinity to positive infinity is allowed. So I'm going to use interval notation because it's the easiest to kind of wrap your head around. So our domain then is from -infinity, and here's where it gets a little bit long, right? -infinity. And this is why you want to write them kind of in order, right? X equals -1 and x equals 2, because then you go up to -1, but not including -1. -1, but not including -1, right? So round bracket. And then we join, so we link these things up, the regions, the intervals, we link them up with that U, the union, right? And then you pick right back up at -1, right? So it's just doing a little jump at -1, and all the values that are close to -1, but not equal to -1, those are all allowed, right? And then from -1 up to 2, but not including 2, right? So round bracket again. And then I can pick right up at 2, and then I'm allowed to go to infinity, right? So you just carve out little holes at the values of x that you can't have, right? -1 and 2. Okay, it's going to take some practice, but I think once you've seen a few and you're just kind of like, oh, okay, well, I'm not allowed to have -1, so I need to link them up at -1, but then I can pick right up until I have another value that I need to pull out. Good. So let's do 14. Let's see here. The root. So now, right away, right? I've got a root and I've got division. So what I need to do is I need to figure out, okay, the overlap of all the values that are allowed, and that's my overall domain, which is exactly what we've done, I think, in section 1.1 when we looked at, okay, so we've got a region here and a region here, and the overlap of those two is what, right? So we've done this before, it's just a little bit different, right, how we get those values. So the root of 2x over x plus 1. Let's see if I can remember that. Root of 2x over x plus 1. So here, in terms of our domain, right, we need 2x to be greater than or equal to 0. So usually this is how I kind of formulate my domain calculations, is I take what's underneath the square root and I say, okay, well, it has to be greater than or equal to 0. I can't take the square root of a negative, right? And then here at the same time, because I don't have a quadratic, what I'm going to say is that x plus 1 can't equal 0. right? That's going to be the easiest way to deal with this one. Okay. So I can't divide by 0 and I can't take the even root of a negative number. And that's what I've done here. Now, we haven't talked about inequalities that much yet. That's in the next section that we're heading into. We jump ahead quite a bit. We don't do 1.6. 1.7 is just word problems, which might be fun to look at. But there are typically no word problems on the final exam. So in the interest of covering chapter 1, I've cut it. But it might be fun to look at some word problems from different fields. All right, so inequalities is section 1.8, which we're going to do later. But here, right, we may as well talk about it. It has to be greater than or equal to 0. Okay. So we can treat this as an equal sign. The only problem is if we're multiplying or dividing by a negative, the sign switches there. That's section 1.8. That's all we're going to do in 1.8, basically. So we'll get there. But because we're dealing with positives here, it's not going to be a problem. So to solve this, right? So I need 2x has to be greater than or equal to 0, which means x has to be greater than or equal to 0. Why did that happen? Okay. I can treat it like an equal sign, which means I have to, if I'm solving for x here, I need to divide both sides by 2. 0 divided by 2 still makes 0. But if we check it, right? X has to be greater than or equal to 0. It still works, right? No surprise there, because 2x, if x is 0, well, 2 times 0 is 0, so that's fine, right? And then as long as x is positive, 2 is positive, so positive times a positive is going to yield a positive, right? So as long as x is positive, which is what we're saying here, then we're safe, right? So here's our first condition that we need to satisfy, okay? And x plus 1 cannot equal 0, which means if I'm solving for x here, again, this is an inequality, not equal to, but you can just treat it like an equal sign. Then x cannot be equal to negative 1. Okay. The overlap of these two, okay, you can draw them on a number line. In fact, let's do it right now. Whoops. So here I've got 0, here I've got negative 1, right? So here I'll draw this one in blue. X has to be greater than or equal to 0. So it's allowed to be equal to 0. And it has to be all the values that are greater than it. This one I'll draw in orange. Orangey glad I didn't say banana. X can't be equal to negative 1, right? So all values are allowed except for at negative 1. All right, so you can still draw these out like we were doing earlier, but eventually you won't need the graph, right? So eventually you won't need the number line, but the overlap here of both of these is just x is greater than or equal to 0, right? So here, the overlap dealing with a page break here, because this is the end of the review, long review today. I wanted to keep it on the same page. That's why I'm scrunched here. So then the domain, domain. The domain is an interval notation, right? I've decided, okay, I'm allowed to be 0, but nothing less than 0 and everything greater than 0. So from 0, including 0, up to infinity. End of review. Okay. So a lot happened last day, right? And it's all going to come back into play a lot. Okay. So let's see here. Let's go back to our 1.4 nodes. So the domain is really important to kind of keep an eye on inputs that are allowed and not allowed, okay? So let's see here, 1.4. Rational expressions, we said, have the form of a polynomial over a polynomial, right? And so when we're dealing with rational expressions, we've talked a lot about fractions before, right? And we established the rules of fractions. I need a common denominator in order to add or subtract fractions, right? If I have a fraction equal to a fraction, I can cross multiply, right? And so those rules still apply. So one thing, so same thing with factoring here, right? You have to have a common multiple in both the numerator and the denominator in order to cancel so in order to cancel, cancel, there. A value or terms, okay, in a fraction, and this is old news for us, right? So in a fraction, we need to have that as a common multiple in both the numerator and the denominator. It must be a common multiple or factor, if you prefer, or factor in both the numerator and the denominator. Okay. So let's do a quick example of that. Let's do, okay. First thing, when you're scanning here, you're seeing a lot of quadratics, right? We know how to factor quadratics. In the interest of time, I'm going to leave those for you to do. You've got the solutions, so I don't feel like I'm leaving you out to dry here, but right, so notice a lot of quadratics. Even this one here, 23, where the highest power is x to the power of 3, but notice you've got x to the 3, x squared, and minus 6x. So you could pull out a common multiple of x, and then you'd have a quadratic times x, right? And so you can still kind of manipulate things to make quadratics, and you know how to factor quadratics using the quadratic formula, right? And so let's see here. Thanks. Let's do, I feel like we just did we just factor x squared minus x minus 2? I feel like we did. So let's do, I want one with a multiple. All right, let's do 15 first, just to get a warm up in. 5 times x minus 3 times 2x plus 1 divided by 10 times x minus 3 squared. So this x minus 3 is squared, right? Which is technically x minus 3 times x minus 3. Sometimes it's good to remind yourself of that, right? And so here, when you're canceling, right, you see a multiple of x minus 3 because this is all multiplied across here. So x minus 3 is a common multiple. And what we end up doing typically is I just scratch off the 2, right? And the x minus 3 to the power of 1, right? Or, so this becomes 5 times 2x plus 1 over 10 times x minus 3, right? Or if you prefer, 5 times x minus 3 times 2x plus 1 over, 10 times x minus 3 times x minus 3, if you wanted to emphasize that you're only canceling one of those, right? You end up at the same spot. Now what you would do is you would check to see, depending on, it doesn't matter which one. Let's say you work on this one. 5 over 10, you can simplify, right? 5 is a multiple of, or 10 is a multiple of 5, I should say, right? And so 10 you can rewrite as 2 times 5. And so this becomes, so usually that's how I write it, right? I just cross it out and I write the replacement number. And I know that can be confusing maybe in the beginning, but that's why I'm showing you so that you know what I'm saying. 2x plus 1 over 2 times x minus 3. Okay. I could expand this, right, to make 2x minus 6, but there's nothing else for me to factor here, right? I need common multiples, and there's nothing more for me to do here. Okay, so I'm just going to leave it there. No more common multiples, and so I would just leave it. You could expand this out, but I'm lazy, so I'm leaving it. So let's see here. How about we do 21? Because at first it's a little bit funny looking, right? 21, y squared plus y. Then when you write it out, it's kind of like, okay, I see it. Y squared over y squared minus 1. Okay. So if we want to simplify, that means canceling, right? And if we're talking about fractions, right, it means canceling. It means kind of removing common multiples. So what I need to do is I need to figure out a way that I can cancel stuff in here. One thing that I'm going to try first is I'm going to pull out a common y here, right? Y squared plus y, I can rewrite as y times y plus 1. Okay. Now, here, this is a special factoring formula, right? Y squared minus 1. And just as a heads up, you can use any variable that you want here. We're used to using x's, but we're using y's. We can use t's, are pretty common. For time, doesn't matter. Right? They all behave the same. So y squared minus 1, let's just use the quadratic formula to solve it, right? This is a quadratic. Quadratic with a equals 1, right? B equals 0. There's no x term, or in this case, y term. There's no y to the power of 1 term. And c equals negative 1. Okay. I'm not solving for x anymore. I'm solving for y. So y is going to be negative b plus minus the square root of b squared minus 4ac over 2a Like I said, you'll probably have this thing memorized in no time. If you don't, probably a good thing to have always in front of you when you're working on your math, right? To have that quadratic formula so that you can always, you know, remember it and have it available at all times. Okay, we use it a lot. So if I'm factoring this thing, right, I need to find the roots, and then I use those roots to make my factors. So here we go. B is 0, so negative 0 is just 0, plus minus 0 squared minus 4 times 1 times negative 1 over 2 times 1. Okay. So this is the square root of positive 4, right? Negative 4 times negative 1 makes positive 4, so 0 plus minus the square root of 4 over 2. So I get y is 0 plus minus the square root of 4, I'll just write 2, divided by 2. So 0 plus minus 2, again, this is going to give us one of those bouncing off the x-axis, but we're calling it y. That's confusing, but it's okay. It's okay. So then y is 0 plus 2. We can write it out and just convince ourselves. Oh, it's not actually. Good thing I wrote it out. And y equals 0 minus 2 over 2. Oops. So y is 2 over 2, which is 1, and y is negative 2 over 2, which is negative 1. Aha. Okay. So this is where it gets a little bit confusing, right? So to factor this thing, right? So now we can use these roots to factor, right? So what we have is we want to factor y squared minus 1. Y squared minus 1 is going to be the same as, oops, I tried to use x. That's wrong. Y from here, if y is equal to 1, right? So if this y is equal to 1, the whole thing should equal 0, right? So what I do is I take the opposite. So y minus 1 is a factor, right? Because if I plug in y equals 1 here, 1 minus 1 makes 0. Okay? I say it becomes confusing because here we've got y equals negative 1. So then the factor for that is going to be y plus 1, right? You end up doing kind of the opposite sign of what your roots are. So this one is making this factor, and this one is making the second factor. Just keep those straight, right? It could be confusing because here you've got y equals positive 1, and here you've got y equals negative 1, but they actually belong to the opposites. Okay. This is also a special factoring formula. It's the one that I was reaching for earlier, right? In section 1.3, we talked about special factoring formulas. And if you have something of a squared minus b squared equals a minus b times a plus b, you could have gone straight there, right? And so here, oops, let me just grab this in here. Or notice that y squared minus 1 is the same as y squared minus 1 squared, which is a special factoring formula, which is y minus 1 times y plus 1, which is exactly what we found, right? So either way, you're going to end up, but that's what I mean. So I don't actually memorize these special factoring formulas. Obviously, I flubbed it earlier. It's a squared minus b squared that we can do, not a squared plus b squared. So these might be nice to have handy, but ultimately you can just apply the quadratic formula and it'll require a little bit more work. You guys won't believe how much snow we're getting right now. It's crazy. Right? Using the quadratic formula will always work. If you have a quadratic, you can always just kind of chug through and get those factors, right? And so I know that's not the most elegant way, but for me, I like to have something that I can always do, so I'm not always kind of, oh, is that a special factoring formula that I should remember? No, not for me. If you have these memorized, then great, right? Use them, that's fine. Then you can just say y squared minus 1 equals y minus 1 times y plus 1 by a special factoring formula, and then you're done, right? But for me, if you just use a quadratic, that's what I prefer to do, but we're allowed to do whatever we want. So what we have up here, right, is I've factored this to become y minus 1 times y plus 1. See work below. Okay. Only because I started and I didn't want to leave it hanging there. Okay, and because I've obviously forced myself out, I'm going to keep going with the equal signs across here because we're so close. So here I've got a y, and then I've got y plus 1 and y plus 1 as a multiple in both the numerator and the denominator. So what I'm going to do is I'm going to be able to cancel that. And so y plus 1 and y plus 1, those are going to cancel. So as soon as you have a fraction, there is usually some sort of common multiple, and once you factor a little bit, it'll be clear. Leaving you with y over y minus 1. There's nothing I can do here, and so it's simplified, right? You could rewrite this as, nah, I'm just going to leave it. Just leave it. Okay. Great. All right. So we're going to keep dealing with fractions. Remember, we spent a lot of time working with fractions. So now when we make the extension to kind of having terms of, x plus 1 or whatever in there, it's not going to change anything. Oh, I don't know why I went there. Okay, so here, right, work through these, make sure that you're able to factor things out and simplify. That's going to be really useful later on. Okay. Multiplying and dividing rational expressions behaves the exact same way, right? Rational expressions where we have a polynomial over a polynomial, we can still multiply and divide those things. In fact, I want to do 34 just for practice. Rational expressions follow the same rules for fractions as we established. Can't remember what section that was earlier. So I cheat and I just say earlier. Okay, so we can do, which one did I say I wanted to do? 34. Okay, so 34, I've got this, I'll zoom in a little bit here. I've got a rational expression divided by, and that's why I picked this one because it's got the weird notation. So it's divided by, and then another rational expression. it can work with these. Now when I talk about common denominators, for example, x plus 3 is a denominator. And in this case, 2x squared plus x minus 15 is a denominator, right? And so when I need common denominators, those are the ones I need. A little bit trickier than just a number, but it behaves the exact same way, okay? So we've got 34. I've got 2x plus 1 divided by 2x squared plus x minus 15. Now what I'm going to do right away is I'm going to rewrite it so that I can visualize a fraction over a fraction, right? Because then I know I have to flip the denominator and then I multiply. Remember, I make that middle line slightly longer just to emphasize that, hey, this is a fraction over a fraction, right? And that's just to help you kind of see what's going on. Over 6x squared minus x minus 2 divided by x plus 3. So what I have to do here, right, I have to flip this denominator and I multiply the two. When I do that, I get 2x plus 1 divided by 2x squared plus x minus 15. To show that this is one fraction multiplied by another fraction, I'm going to put brackets around these terms, right? And then I'm going to multiply. And again, I'm going to put brackets around just so I see that I need to expand this thing. So here, right, x plus 3 over 6x squared minus x minus 2. So I get x plus 3, right, once I flip it and multiply over 6x squared minus x minus 2. Okay. So, do I see anything kind of glaringly obvious that I can cancel right away? Well, I would have to expand this out, right? So this becomes 2x squared plus 6x plus x plus 3. That's not one of these terms, right? What I could do is I could go through, I don't know if it says to simplify, and simplify, rats. Okay, so why did I say rats? I'd have to use the quadratic formula here and the quadratic formula here to figure out if I've got any multiples that I can cancel. So what I'm going to do is I'm not going to expand this out, right? So in my mind, just to walk you through how I see this problem, first thing I do, because I don't want to factor these two things, right? That's two quadratic formulas that I need to do side by side. That's a lot of work, right? Trying to avoid that, in my mind, what I did was I said, okay, well, can I expand this top one, the numerators, can I multiply those out, right? I'm multiplying fractions, so I can just multiply across. Can I expand this out to be one of these quadratics? And then I could just cancel it, right? Or be some multiple of one of these quadratics. It didn't work out, right? I end up with 2x squared plus 6x plus x, so plus 7x plus 3. That's not one of these, right? And so unfortunately, what I need to do is I need to use the quadratic formula in order to try to cancel something here. Okay. This is a quadratic. How about I just say quad with a equals 2, b equals 1, and c equals negative 15. And here, this is also a quadratic with a equals 6, b equals negative 1, and c equals negative 2. You can see where a quadratic calculator function would be handy, right? All right, that's okay. we're going to get a little bit quicker calculating these quadratics, right? And so first thing I'm going to do is I'm going to factor 2x squared plus x minus 15. Okay. Maybe I'll try to do these side by side just to have it not span so many pages. So here, and maybe I'll just write this in plain old blue, you'll see why. Factor that and factor 6x squared minus x minus 2 over here. Okay. Maybe I'll do dark green. Looks all fuzzy. All right, so here x is going to be negative. So what I'm going to do is I've already listed what the values are here, so I'm just going to jump right in and plug them in. So negative b is -1 plus minus the square root of 1 squared minus 4 times a, which is 2, times c, which is -15, over 2 times a, which is 2. So I get -1 plus minus 4 times 2 times 15, yikes, okay. 4 times 2 times 15 is 120. And that is positive, so 1 plus 120. Oops. Square root of 121. I'm just going to see if that is, it is 11, so that's great. Over 4. So this -1 plus minus 11 over 4. Okay. Notice that I'm moving through this thing a little bit quicker, right? Because the end goal is to factor this thing. And so it's just going to be a kind of a mechanism to find these roots, right? The roots here are -1 plus 11, -1 plus 11. So x is -1 plus 11 over 4, and x is -1 minus 11 over 4. -1 plus 11, oops. -1 plus 11, I'm just doing it on the side here, is 10 divided by 4, which is 5 over 2, but in case your calculator doesn't simplify it for you, right, I'll just keep it as, well, let's see what the Desmos calculator does. Oops, clear all. 10 divided by, 4. Okay, so it does simplify it. So how about we use the simplified version, 5 over 2. Oops. Right. If you were to use the Desmos app or whatever you're using, right, make sure your calculator gives you the simplified version. Right? That'll just be easier. And x is -1 minus 11 divided by 4 is -3. Okay. Do you remember how we manipulate as soon as we have a fraction here, right? This is the same as 2x equals 5, right? You bring this 2 over here, you have to multiply it over so you don't have any fractions anymore, right? But this is saying 2x is equal to 5 makes 0, okay? And x equals -3. So how do we write this as factors? Well, this becomes 2x squared plus x minus 15 if we rewrite it. So, oops, 2x squared plus x minus 15 is going to be the same thing as, just making sure I wrote it down right, as 2x minus 5, right? So we read these the same way as we did before. Right now we've just got a 2x here instead. So we get 2x minus 5, because when 2x is equal to 5, right? When 2x is equal to 5, this thing has to be 0, which if we force it to be 2x minus 5, 5 minus 5 is 0, right? So that's the trick that we developed last day. And then our second factor here is x plus 3, because when x is minus 3, it has to become 0. So now I've factored that portion, okay? I'm going to do the exact same thing. You can see why I was trying to avoid having to factor this stuff, right? But the more practice we do with these quadratics, the better off we'll be just in general, in math. So 6x squared minus x minus 2, we already established that a is 6, b is -1, and c is -2. So I'm just going to jump right to it here. So x is negative b, which is -1, plus minus the square root of -1 squared minus 4 times a, which is 6, and times c, which is -2. Over 2a, which is 6. This becomes 1 plus minus the square root of 1 minus, and then 4 times 6 times -2 is -48, so plus 48 over 12. Okay. So a little bit quicker, right? So make sure that you're following along. And so 1 plus 48 is, of course, 49, and the square root of 49 is 7. So this becomes 1 plus minus 7 over 12. So x is either 1 plus 7 over 12, and x is 1 minus 7 over 12. 8 over 12 simplifies to 2 over 3, so x is 2 over 3, and 1 minus 7, no, 6 is -6, divided by 12, I jumped the gun, and x is -1 over 2. Now we've got two fractions. Don't worry, we know how to deal with that, right? I'm just gonna scoot this 3 over here, right? I need to multiply it over. If it's dividing on one side, to move it over to the other side, I have to multiply, right? And so what we get here is we get 3x must be equal to 2, and 2x must be equal to -1. Okay. Now I'm going to use these factors, or these roots rather, to factor 6x squared minus x minus 2. So I'm going to rewrite that. So 6x squared minus x minus 2, I can rewrite using these roots, right? 3x is equal to 2 makes 3x minus 2 times 2x plus 1, right? It's going to be 0 when 3x is equal to 2. So when 3x is equal to 2, 2 minus 2 is 0. When 2x is equal to -1, 2x, -1 plus 1 makes 0, right? So it still works, and we can expand this out. And you should expand it out just to check that what you've done makes sense and that it works, right? And so, and if you expand it out, it'll work. So now I've got all these factors that I can write in the denominator. Now, let's see here. I'm going to copy this here. Copy. Paste. I'm going to scoot them a little bit closer together because I need more room here. So this becomes 2x plus 1, I'm not touching the numerator because I wasn't able to expand and simplify. So what I'm going to do is I'm going to keep them factored out, 2x plus 1 times x plus 3. And then what I'm hoping for is that one of these factors, right, or two or more, are going to cancel out here, okay? So when I rewrite this value here, I'm going to replace it with 2x minus 5 times x plus 3. And just to emphasize that, I'm going to use the same color as I used earlier, right? So this becomes 2x minus 5 times x plus 3. And then from the 6x squared minus x minus 2, I have 3x minus 2 times 2x plus 1. These are all being multiplied together, right? What I see right away is I have a 2x plus 1 and a 2x plus 1. Yes, right? So that's what we were hoping for. That's why we factored this thing, right? That's why we went through all the trouble of factoring and the quadratic and whatever. And again, we see that x plus 3, well, x plus 3 is also a multiple down here. So that's awesome, right? What happens is this 2x plus 1 cancels with this 2x plus 1. And then this x plus 3, because they're all multiplied together, it only works if they're multiples, right? What's left in the numerator? Just 1, right? So you want to be careful that you keep that 1. And then in the denominator, you have 2x minus 5 over 3x minus 2. There's nothing else to do there. And so what we're left with here is this becomes 1 over 2x minus 5 times 3x minus 2. Whee! A lot of work, right? Lots of practice, right? So how about we take a little 6-minute break until 9:10. Now it's a 5-minute break. Let's keep going. Okay. Wait. Like it never happened. All right. So let's see here. So what we're establishing here in this section is that even when you have something kind of huge like this, right? This is a quadratic over a quadratic times a quadratic over a quadratic. Ugh, no thanks, right? I don't see any clear cancellations that I could do. I'd have to have the same quadratic in the numerator as I do in the denominator. I do not in either of these cases. And so all I'm left to do is factor these things using probably the quadratic formula. Unless you see what they factor to, then just go for it, right? But for me, I always end up having to use the quadratic formula. And right, so lots of practice, a lot of work. You'd have to factor them all individually, and then presumably some terms will cancel out and then it'll be simplified. Okay, so I'll leave those for you to work on your own because it is really just a lot of practice. What if we have to add or subtract fractions? Now, of course, if we have the common denominator, then we can go right ahead. But for all of these, right, I don't have a common denominator, and so I need to find that or force that common denominator rather. And we do it the exact same way that we did. So even though we've got these terms, these essentially polynomials, right? X minus 3 is a polynomial, for example. So now when I'm forcing this common denominator, I need to look at, so let's do 41 together. Okay, so here, just for some practice, right? I need a common denominator. I've got a denominator of x plus 5 and a denominator of x minus 3. So my common denominator that I'm going to force is just the 2 multiplied together. So let's do 41 here. Oops. I've got 1 over x plus 5 plus 2 over x minus 3. So we need a common denominator. And I'm going to force it to be x plus 5 times x minus 3. Okay. Which means that, okay, this first term has to be multiplied by x minus 3 over x minus 3, right? So same idea that we were applying before when we were forcing that common denominator, right? And then the second term has to be multiplied by x plus 5 over x plus 5, right? So this becomes 1 over x plus 5. And I'm going to put brackets around it just to emphasize that x plus 1 holds together. That's one thing, right? And then x minus 3 is another thing. Okay. And so I'm going to multiply it by x minus 3 over x minus 3. Right? That trick of multiplying by 1, a convenient value of 1, to force what we need in the denominator, right? Without changing the expression. Plus 2 over x minus 3. And then again, I need to multiply by x plus 5 over x plus 5. And just to emphasize, I'm going to put brackets around the x minus 3. And maybe they shouldn't be light blue. Maybe they should be dark blue. There. Doesn't matter. Okay. So now I've got this common denominator, but I've also kind of made a little bit of a mess up top here. So I need to expand that out and simplify. Okay, but now I'm able to put it in the same numerator. So I've got 1 times x minus 3 is just x minus 3, plus 2 times x plus 5. And this is all over x plus 5 times x minus 3. So when I expand this out, right, I get x minus 3 plus 2x plus 10. So I'm going to work it a little bit more. X minus 3 plus 2x plus 10 divided by x plus 5 times x minus 3. The reason I'm not expanding the denominator is because usually if we're simplifying, we want it factored, right? And so I'm going to keep it factored just to see if I'm able to cancel anything. Okay. I get 3x minus 7. Okay. There's nothing glaringly that I can simplify here, right? X plus 2x is 3x. Negative 3, oh sorry, plus 7. Negative 3 plus 10 is 7. So 3x plus 7 over x plus 5 times x minus 3. Now, if I was able to factor this in any way to make it look like either x plus 5 or x minus 3, I would do that. I don't see a way that I can easily do that, right? To manipulate 3x plus 7 to look like one of these terms so that I can cancel it. So I'm just going to leave it there. I'm done. Okay. Good. That final step that I took there and saying, nope, that's it, I'm done, that requires practice. right? So getting here and seeing, okay, can I quickly kind of pull out a common factor to make it look like x plus 5 or x minus 3? No. Okay, then I'm done. Right? But that's where we're going to get you to. Okay? Good. So multiplying fractions, adding fractions, subtracting fractions, it all behaves the same way as when we just had numbers, even when we've got these kind of bigger fractions, right? These rational expressions. But the rules of the road all stay the same, right? So even when you have something like this, right? And maybe let's do this one. Okay. One thing that you might recognize, right, is the x squared minus 1. You can rewrite as x squared minus 1 squared, and then that becomes a special factor, right? X minus 1 times x plus 1. Okay, so that's probably the one that I rely on. And then x plus 1. So let's do 58 together, copy. Okay. So what I need, so I have x plus 1, and then I've got x plus 1 squared, right? And then I've got x squared minus 1. So what you can do is you can force this common denominator by just multiplying each term by whichever denominator you're missing, okay? So we can do, all right. We can use x plus 1 times x plus 1 squared times x squared minus 1 as our common denominator. Okay. Or what we can do is we can rewrite this x plus 1. Here's x plus 1 again, right? So this little guy just needs to be multiplied by x plus 1 again to make it look like this. But then we also need to incorporate this x squared minus 1. So you can go ahead and just force it like this. Okay, so which would look like this. 1 over x plus 1. Okay, and then to force that common denominator, and maybe this is how we do it, right? So I just want to show you some tricks of the trade, right? But if you wanted to do it how we're about to do it just now, that's totally fine, right? It's a little bit more work, but things will cancel out and it'll be hunky-dory anyways. So times x plus 1 squared over x plus 1 squared times x squared minus 1 times x squared minus 1. Okay, so each term gets multiplied by the missing value, right? Missing value from our common denominator that we've determined here. Minus 2 over x plus 1 squared. So what's missing here is an x plus 1 over x plus 1 times x squared minus 1 over x squared minus 1. Okay. Plus 3 over x squared minus 1 times x plus 1 over x plus 1. Notice that I'm just kind of scanning, right? So now I have this x squared minus 1, so I need the x plus 1 over x plus 1 and x plus 1 squared over x plus 1 squared. Good. You can do that, right? Now you've got this common denominator, that you forced. It does mean that you need to simplify up top here, right? So what I'm going to do is I would suggest that you don't expand quite yet until you've simplified this thing as far as you can, and to see if you can maybe pull out some common multiples and factor them out. I guarantee you there will be some, because we've got this x plus 1 and x plus 1 squared, so those will cancel. Okay. Or we can factor the denominator to simplify slightly. Now, it doesn't simplify it a lot, so if you wanted to just kind of keep going with this, that's totally fine, right? But what we have here is we have, okay, we've got x plus 1 and then x plus 1 squared. Well, I just need to multiply by x plus 1 squared. And then here, x squared minus 1, x squared minus 1, I can rewrite as x minus 1 times x plus 1. Right? And you can check it, right? X squared plus x minus x. Okay, so that goes away. And then negative 1 times 1 makes minus 1. So, okay, good. Right? Because technically this is x squared minus 1 squared. 1 squared is just 1. Okay. Okay. So then what we have is we have 1 over x plus 1 minus 2 over x plus 1 squared plus 3 over x minus 1 times x plus 1, right, from up top here. So now my common denominator, I've got an x plus 1. I've got a multiple of x plus 1 in each of these, right? So x plus 1 here, I've got x plus 1 squared, right? In fact, maybe I'll write it out like this, right? X plus 1 squared is x plus 1 times x plus 1. Fine. So now I've got x plus 1, x plus 1, x plus 1, right? I need another x plus 1, and I need an x minus 1, okay, to get this common denominator. And so what I have, right, if I need to force a common multiple, then I can extract a common multiple of x plus 1. Common multiple of x plus 1, right? So what we get is this becomes x plus 1 times 1 plus x plus 1 plus, hey, no, I'm multiplying these things. I don't need to add. Haha. Sorry, guys. I better write it out properly. So x plus 1 times x plus 1 times x plus 1 that's just doing the same thing that we did before. What am I trying to do here? Why does it work in my head? And then when I think it, or when I say it, so here, to make this first term look like this one, I need to multiply by x plus 1. And to make it look like the second term, I need to multiply by x minus 1. Yeah. So x plus 1 times x plus 1 times x minus 1 is going to be my common lowest common multiple. Let's just say it that way. Yeah. As you might guess, I would probably use this one. It's more work, but here you have to think, okay, I've got an x plus 1, and I need to make it be able to look like each of these, right? So I need to multiply by x plus 1 again, okay? And then here I've got the x plus 1, so then I need the x minus 1. This becomes, I'm gonna run out of room. Put it down here. 1 over, sorry guys, I managed to flub it again. Maybe not again, I don't know. There. So that first term, right, is going to be times x plus 1 times x minus 1. Because if I pull out this common multiple here, right, to make it look like this denominator, I've got x plus 1 times x plus 1. Okay, so I've got that here. And then I need to make it look like x minus 1 times x plus 1, which I have here. Okay. Minus 2 over x plus 1 squared let's do x plus 1 times x plus 1 times x minus 1. Uh-oh. My brain's not working today. X minus 1 times x minus 1. My recommendation, after me floundering, just do this way, right? Just force it. All right. Plus 3 over x minus 1 times x plus 1. The only thing that's missing is another x plus 1 over x plus 1. Okay. So now this becomes x plus 1 times x minus 1. So I'm not going to expand the numerator, but I am going to collect them all in the same numerator and just see if I can simplify anything. Minus 2 times x minus 1 plus 3 times x plus 1 over that common denominator of x plus 1 times x plus 1 times x minus 1. Okay. I don't see anything that I can, I've got x plus 1 here and an x plus 1 here, and I've got an x minus 1 and an x minus 1 here. So I could do something maybe, let's see here. Nothing really nice pops out at me. Let's try it, right? What am I trying to do? I'm trying to extract multiples here that I can cancel potentially with some of these or one of these. So I can have x plus 1 only because I feel like it should simplify a little bit more. Maybe what I'll do is I'll try expanding this out to see what happens. So I'll get x squared minus x plus x goes away, minus 1 minus 2x plus 1 plus 3x plus 3 over x plus 1 times x plus 1 times x minus 1. Of course, if you prefer to write x plus 1 squared, that's fine. I just want to see them. This becomes x squared Minus 2x plus 3x is plus x. So x squared plus x. Negative 1 plus 1 plus 3. Like that. What's something that adds to... So you could use the quadratic formula here to factor this thing and see if it cancels. I'm actually just going to leave it here because we need to move on, but we have the tools, right? Maybe we should do it. Right, it has to add to positive 1 and multiply to 3. I don't know. That one never worked for me, right? When I have to think about, okay, it has to, unless it's like very, very obvious. It didn't work. This becomes x is negative 1 plus minus, so I'm just going to do it on the side here, the square root of 1 squared minus 4 times 1 times 3 over 2 times 1. Negative 1, okay, so, and then 1, no roots. Plus minus 1 minus 12 is negative 11. No roots. What does that mean in this case? Can't be factored. All right, so let's see here. Let's just check. How can I check that this is actually true? I can check it by graphing it, right? X squared plus x plus 3. Therefore, no factors. Okay, so just to kind of make that connection. Let's graph this. X squared plus x, making sure I didn't screw something up, but it looks okay. X squared plus x plus 3. If we graph it, oops, that's a different class. X squared plus x plus 3, it's above the x-axis, right? So notice that it doesn't actually cross the x-axis. So there are no values that make this thing 0, and so there are no roots. Phew, that's what we found, right? So, so it's all jiving. Okay, so if you do find something like this where you're like, I think there's no roots and therefore no factors, you can always graph it, right, to make sure that it doesn't cross the x-axis. Then we're simplified. That's great, right? If there are no factors, there's nothing I can possibly cancel down here. So then we're done. Okay. Where is it? There. So compound fractions. Compound fractions are just things where you might have a fraction over a fraction, but you first have to find that common denominator. So this is kind of the same thing that we've been doing. So just looking at maybe 62 here, we were just dealing with something like this, right? Where I need to find a common denominator, and then I need to find a common denominator down here, right? So now I need to work both the numerator and the denominator independently, and then when I put them together, then I can have a fraction over a fraction. I flip and multiply. We've done these moves, but with numbers before, right? We did 1 plus 1 over 3 over 1 minus 1 over 2, right? And so we've done this with numbers. Now we've just made it a little bit trickier, right? Because we have this c minus 1 and c minus 1 down here. So we need to find that common denominator before we can keep going. So how about for compound fractions, let's do 62 there. So we've got all the rules for our fractions established already, and we just need to keep them straight in our minds. And then just kind of treat c minus 1 as if it's one thing, treat x minus 4 as if it's one thing, x plus 1 as if it's one thing, x plus 3 as if it's one thing, and then we're just back to where we were before. All right, so 62. I've got 1 plus 1 over c minus 1, all divided by 1 minus 1 over c minus 1. So to simplify this, I need to have a common denominator in the numerator and a common denominator in the denominator, right? So I need to simplify these things independently. So what I get, right, if I need a common denominator, I'm going to use c minus 1. So same thing here, 1 times c minus 1 over c minus 1. Make sure you're always multiplying by 1, right? Plus 1 over c minus 1, which I'm going to put brackets around it just to emphasize that it's one thing. And then 1, again, I'm going to use c minus 1 as my common denominator. And then minus 1 over c minus 1. I can simplify the numerator and denominator individually. So this becomes 1 times c minus 1 is just c minus 1 plus 1 over c minus 1 divided by c minus 1, if I can write it properly, minus 1 over c minus 1. Now we're just back to a rational expression over a rational expression, right? So fraction over fraction can flip and multiply. First, I'm going to simplify this a little bit, right? Because this becomes c minus 1 plus 1, which is just c over c minus 1. Oops. C minus 1 minus 1 is c minus 2 over c minus 1. I'll make this a little bit longer, just to emphasize. But now when I flip and multiply this thing, I flip the denominator. So I get c over c minus 1 times c minus 1 over c minus 2. Notice that I've got this c minus 1 as a multiple up top and a c minus 1 as a multiple in the denominator. Those are going to cancel. Right? Didn't have to factor anything. That's nice. And so what I'm left with is I'm left with c over c minus 2. Okay. So definitely you'll need to work on these things, right? But just remember those rules for the fractions that we've established and we've worked on, common denominator, flip and multiply, right? If you're dividing fractions, those still apply. And you just need to kind of expand it a little bit and make it for terms like c minus 1 instead of just a number like 3. So same deal, right? We've got these kind of expressions found in calculus, and so later on, right, what we're building towards is simplifying things like these here, right? And so this is pre-calculus after all, right? So what we're working towards is working on simplifying something like this. Now, I'm going to leave these for you to work on your own, right? And just kind of see you've got the solution. So I'm not, leaving you out to dry. But then as review next day, because we're kind of getting towards the end here, for review next day, which one do I want to do? Let's do 81 for review next day. And I'll try to remember it because I might forget. But before we go, I want to talk about rationalizing the denominator and the numerator. But 81 is going to be a good review question. okay, for us to start with next day, and then we can get into inequalities finally. So rationalizing the numerator or the denominator, okay, whoops. What we mean by rationalize, and we've already rationalized some values, right? We rationalized, we put things into standard form. I can't remember when exactly, but we did. So what we do is, if you have something like a value plus minus a square root, right? Then what you can do is, if you want to move this square root from the denominator up to the numerator, you multiply by the conjugate radical. Now, the conjugate radical, so if you have a plus b times root c, the conjugate radical, the only difference here is that you have a minus b times root c. So I'm going to actually bring in this whole thing into our notes and cheat a little bit. Okay. So notice, right, to remove, actually it doesn't really remove, to move the square root, when given a term like a plus b root c, we multiply by the conjugate radical. We multiply by a, and I'm just going to emphasize that the only difference here is that you have minus instead, b root c. Okay. Notice that when we work this out, a plus b root c times a minus b root c, when we multiply it out, we get a squared minus b squared times c. Notice that that root c is gone. But what happens when we multiply by a minus b root c, we have to do a minus b root c over a minus b root c. So really what happens is you're just moving that square root to a different spot. So from the denominator to the numerator, or from the numerator to the denominator. The reason we do that is maybe to be able to cancel something, or in calculus in my class on Wednesday, we're going to use it to be able to kind of manipulate something. So going from where things don't work until, and then we kind of manipulate it by rationalizing, and then we're able to change it to something that kind of works. Okay, and obviously you'll have to stay tuned to see what that looks like, but let's do some examples here. So whether you want to rationalize the denominator or rationalize the numerator, right, it just depends on where do you have the square root that you want to move. So here we're told to rationalize the denominator, right? In the other section, it says to rationalize the numerator. Now, what you want to do is you just take, let's do 87 because it's kind of funny looking, right? So I want to remove any square roots from here, okay? And if I have something plus a root, right, then I multiply by that something minus the root. So what this looks like, 87, we have 2 over root 2 plus root 7. Okay. The conjugate radical here, the conjugate is root 2. The terms stay the same. It's just if you're adding here, then you're subtracting. And if you're subtracting, then you would be adding in your conjugate. So here, so what we end up with here is this becomes 2 over root 2 plus root 7. And then I multiply by my conjugate radical, but what I need to do is I need to multiply by 1, right? And so this times root 2 minus root 7 over root 2 minus root 7. Okay. If you expand this out, this becomes 2 times root 2 minus root 7. I'm just going to keep it as a multiple right now. And then remember there's brackets around all these. So I have root 2 times root 2, that's 2. Root 2 times negative root 7 is negative, so minus root 2 root 7. But then I have plus root 2 root 7, so that's going to go away. And then plus root 7 times negative root 7 puts me at minus 7. Okay. So notice how all I've done is I've shifted the square root from the denominator up to the numerator. So this becomes, this becomes 2 root 2 minus 2 root 7 if I just expand it out over negative 5. Notice rationalizing simply moves the square roots from the denominator to the numerator. Okay. And then what I want to do is I'm just going to make a note here. We said do 81. Copy. This is more for me than for you. Do 81 as review next day. Okay, so we're not going to work too much on rationalizing, but it is important to know what it is and to see that all you do is you just multiply by the conjugate, and then it shifts the roots from the denominator to the numerator, or if you're rationalizing the numerator, from the numerator to the denominator. Anyways, I'm out of time. So try some of these expressions found in calculus questions, and then we'll do 81 together. Notice that we've got fractional exponents. Yuck. Right. Thanks, Wendy. It's a bit much. Boom, 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 boom. But that's great. Good, good, good. All right. Well, I'll be around for questions. I do have a class after, but otherwise I'll see you Wednesday, or not Wednesday, Thursday. Hopefully you've stopped listening.